Yeah, this is Ashutosh Singh, assistant professor in GIMS Technical Campus. This is transfer. Today, in this lecture, we will discuss about the heat transfer through fin and the basic concept of unsteady state heat transfer rate. Meaning of unsteady state heat transfer. So let us discuss. If the temperature of a body does not varies with time, it is said to be a steady state. But if there is a drastically change its surface temperature, or it attains an equilibrium temperature or a steady state after some period, so therefore during this period the temperature varies with temperature and the body is said to be an unsteady state or transient state. Therefore, the term transient or unsteady state are phenomena in which time is dependent variable. So, it is a very important point. In case of unsteady state, time dependent is very important parameter. Therefore, the steady state is thus the limit of transient temperature distribution for large value of time. So we can say conduction of heat in unsteady state refers to the transient condition wherein the heat flow and the temperature distribution at any point the system varies continuously with time. So therefore in many heat application, yeah, in many conduction problem in contact in engineering application involves time as a independent variable. The goal of analysis is to determine the variation of the temperature as a function of the position and time, or we can say T is a function of x comma T within the conducting body. Therefore in general we deal with conducting bodies in a three-dimensional space in a suitable set of coordinates. The goal is to predict the evaluation of the temperature field for future times. So we can write the mathematical expression for unsteady state heat transfer, that is rho Cp del T by del T is equal to del K delta T plus Gr, where del T divided by del T is equal to unsteady state heat transfer parameters, and Cp and rho are the specific heat and density of the fluid. So therefore unsteady state heat transfer generally used in different applications: IC engines, automobile engines, heating and cooling of metallic bodies, cooling and freezing of foods. These are the basic example of unsteady state heat transfer rate. So therefore in unsteady state heat transfer rate temperature varies with time. So time is very important parameter. So on the basis of unsteady state heat transfer we calculate the lumped system, or we calculate the lumped analysis. So lumped analysis is a part of unsteady state heat transfer rate. So what is lumped analysis? Lumped analysis, if the temperature of the bodies remains relatively constant with respect to distance, or can be treated as a lumped system analysis, or heat transfer is a function of time only. Mathematically we can express this definition: the temperature is a function of time. So therefore we can use some certain dimensionless number. One of these are Biot number, Fourier number. So in case of lumped system analysis, the typical criteria for the lumped system analysis is the Biot number value is always less than 0.1. Therefore in heat transfer analysis some bodies are observed to behave like a lumped, whose interior temperature remains essentially uniform at all times during a heat transfer process. The temperature of such bodies can be taken to be a function of time only, that is T is a function of time. So heat transfer analysis that utilize this idealization is known as lumped system analysis, which provide great simplification in certain class of heat transfer problem without much sacrifice from accuracy. In case of lumped analysis, we assume a copper ball, we assume a plate, we assume a spherical ball. So therefore, consider a small hot copper ball coming out from an oven, and measurement indicates that the temperature of the copper ball change with time continuously, but it does not change with much portion at any given time. Thus, the temperature of the ball remains nearly uniform at all times. Or in another form, we can talk about the temperature of the ball with no reference of a specific location. In case of lumped analysis, we assume that the surface of the body are maintained at a equilibrium temperature. All bodies have a finite thermal conductivity, and there will be always a temperature gradient inside the solid whenever heat is added or removed. However, for solid of large thermal conductivity with surface area that are large in proportion to their volume, like plates, like thin metallic wires, therefore, in case of lumped analysis, the internal resistance in case of conduction, that is known as L upon Ka, can be assumed to be small or neglected in comparison with the convective heat transfer resistance. Therefore, typical example of this type of heat flow rate are heat treatment of metal, or we can say time response of thermocouple and thermometer, etc. Lumped analysis. So consider a body of arbitrary shape of mass m, volume v, surface area a s, density r, and specific heat Cp, initially at a uniform temperature Ti. When at time is equal to 0, the body is placed into a medium at a temperature which is maintained at T infinite, and heat transfer take place between the body and its environment with a heat transfer coefficient H. So H is a heat transfer coefficient in case of convection. For the sake of discussion, we assume the arbitrary temperature T is always greater than Ti, that is the initial temperature when time is equal to T is equal to 0. So, but the analysis is equally valid for the opposite case. We assume lumped system analysis to be applicable so that the temperature remains uniform within the body at all the time and change with time only. Mathematically, we can say T is a function of time. During a differential time interval delta t, we assume a small incremental change in time, that is known as dt, and the temperature of the body rise by the differential amount del t. An energy balance equation of the solid for a time interval dt can be expressed as the following equation. This is known as h multiplied by a is multiplied by t infinite minus t whole multiplied by dt is equal to mcp dt, or we can say the transient response of the body can be determined by relating its rate of change of internal energy with convective exchange at the surface. Therefore, del t minus t infinite divided by t minus t infinite is equal to minus has divided by rho v cp multiplied by t, where v is equal to volume of the body and Cp is equal to specific heat of the body, H is equal to heat transfer coefficient, and As is equal to surface area of the body. So by integrating this equation, we get T minus T infinite divided by Ti minus T infinite is equal to e की power minus Bt, or we can say e की power minus Biot number or Fourier number. This is a mathematical expression for the temperature distribution in case of lumped analysis, where T suffix T is a instantaneous temperature at any point, T infinite is equal to temperature of the surrounding bodies, and Ti is equal to the temperature of the body when the time T small t is equal to 0. Is lumped analysis. So finally, the equation of lumped analysis is ln t minus t infinite divided by ti minus t infinite is equal to e की power minus Biot number and Fourier number. The quantity rho Vc divided by HAS has the dimension of the time and it is called as thermal time constant denoted by tau delta Th. Its value is indicative of the rate of response of a system to a sudden change in its environmental temperature. So from this diagram, the temperature of the body approaches the ambient temperature capital T exponentially. The temperature of the body change rapidly at the beginning but rather slowly later on. A large value of small b indicates that the body approaches the environment temperature in a short time, or the larger value of the exponent, the value of b, the higher rate of decay in temperature. It is noted that the b is proportional to the surface area but inversely proportional to the mass of the body and the specific heat of the body. This is not surprising since it takes longer to heat or cool a larger mass, specifically when it has a large specific heat. So from this figure it is clear that the large value of B approaches the temperature T infinite exponentially. So the Hessian chart. So Hessian chart is also a very important parameter in case of lumped analysis. The solution obtained for one-dimensional non-homogeneous problem with boundary condition is Cartesian coordinate system using the method of separation of variable have been collected and assembled in the form of transient temperature by Hessian. The given chart are a very useful baseline against which to validate one's own analytical or numerical consumption. So therefore, the Hessian chart provides the temperature history of the solid at its mid-plane, and the temperature at other locations are worked out by multiplying the mid-plane temperature by correcting factor read from the charts. So the value of Biot number, that is Bi, and the Fourier number, that is Fo, are used in a Hessian chart are evaluated on the basis of characteristics parameter, which is the semi thickness in case of plate and the surface radius in case of cylinder and sphere. So this is very important parameter. When both conduction and convection resistance are almost of equal importance, the Hessian charts are extensively used to determine the temperature variation. So we can say that the Hessian chart is generally used to determine the temperature variation when the conduction resistance and the convection resistance are equally important in case of heat flow. The transient temperature chart shown in next slide for a large plane, long cylinder and spherical wall. So therefore there are three charts associated with each geometry. The first chart is determine the temperature T0 at the center of the geometry at a given time T, and the second chart is to determine the temperature of the other location at the same time in terms of T0, and the third chart is to determine the total amount of heat transfer up to a time T. These plots are valid when the temperature is always greater than 0.2. So Hessian chart is a very important parameter to calculate the temperature distribution in case of the conduction and convection resistance both are equal. So the determination of all constant, that is A1, L1, usually required interpolation. For those whose prefer reading charts to interpolating, these relations are plotted and the one term approximation solution are presented in graphical form known as transient temperature charts. Heat transfer through fin. So it is also a very important parameter. So what is the meaning of heat transfer through a fin? So let us start. Whenever the available surface is found inadequate to transfer the required quantity of the heat with the available temperature drop and convection heat transfer coefficient, extended surface or fins are generally used. This practice is found necessary in heat transfer between a surface and the gas, as the convective heat transfer coefficient is rather low in these situations. The fin surface are generally used in different applications. So convective heat transfer between a solid surface and the surrounding colder fluid is governed by the Newton's law of cooling, which states that the rate of convection heat transfer rate is directly proportional to the temperature difference between the hot surface and the surrounding fluid is also directly proportional to the area of contact or exposed between them. So therefore Newton's law of cooling can be expressed as Q convection is equal to HA delta T, where H is equal to heat transfer coefficient, A is equal to surface area, and Ts is equal to the temperature drop. So the convective heat transfer can be increased by either of the following ways. Number one, increasing the temperature difference between the surface and the fluid, increasing the convective heat transfer coefficient by enhancing the fluid flow or the velocity over the bodies, and the last one is increasing the area of contact and exposed between the surface and the fluid. So therefore heat transfer rate can be increased by drastically by using fin application. Different fin application. So fins are extended surface producing from a surface or a body, and they are made for increasing the heat transfer rate by the surface and the surrounding fluid by increasing the heat transfer area. Therefore the fin surface are generally used in air cooled engine, IC engine, refrigeration, condenser tubes, electric transformer, reciprocating or air compressor, automobile radiator, or it can be also used in transformer and electronics equipments, a small capacity compressor, and economizer for steam power plants and electric motor bodies. So there are different types of fin we can use. The first one is longitudinal fin, the second one is radial fin, and the third one is pin fin. Generally in most of the application, longitudinal fins are generally used in IC engine, or in case of 2-stroke petrol engine, or in case of 4-stroke petrol engine. Different types of fin. Fins can be classified on the basis of the surface structure. So the first figure, this is a A. In this case we can classify the fin on the basis of its surface area. It can be classified as 8 types: A, B, C, D, E, F, G, H, I. In case of figure A, it shows the longitudinal fin with rectangular profile. The figure B indicates longitudinal fin with rectangular profile. Figure number C, longitudinal fin with trapezoidal profile. Figure D shows a longitudinal fin with concave parabolic. The figure number E shows a radial fin with rectangular profile. Figure F shows the radial fin with triangular profile, and the figure G indicates the pin fin with cylindrical shapes. Figure H shows the pin fin with tapered profile, and the figure I represents the pin fin with concave profile. So today in this lecture we have discussed transient conduction of heat transfer, types of fin, application of fin. So in next lecture we will discuss about the analysis of heat transfer rate through the rectangular fin.